Okay, so in our last lecture, we introduced the idea of Johannes Kepler, who he was, and his laws of motion. The planet orbits the sun with the sun at one focused ellipse. The line between the planet and the sun sweeps out equal areas and equal times, and the relationship between the orbital period and the distance from the sun. So basically that's what this means. Elliptical orbits speed up and slow down. They go fastest when they're close to the sun, slowest when they're far from the sun, and p squared equals a cubed. So let's go back. Let's investigate the first law. So for the first law, elliptical orbits. So elliptical orbits, actually there's a way of defining how elliptical an orbit is, and that's called eccentricity. Eccentricity is a measure of the difference between the aphelion and the perihelion. Now remember, aphelion is, remember we talked about this before, aphelion is farthest from the sun and perihelion is closest to the sun. Okay, if it's you can also elliptical orbits around Earth, and then in case it's apogee and perigee. Okay, you can have orbit around Jupiter, and it's apjove and perijove. Okay, and so the ap means the far part of the orbit, and the perihelion is the near part of the orbit. Okay, so the relationship is eccentricity, that's how far out around it is equal to aphelion minus perihelion divided by aphelion plus perihelion. If aphelion equals perihelion, then the numerator is 0. You divide anything by 0, that's 0. So eccentricity of 0 means perfectly round orbit. And as the orbit gets more and more elliptical, the eccentricity gets bigger and bigger. Okay, so this diagram you can actually see on page 85 of your textbook. And so let's do an example here. Let's say that you have an orbit here, and let's say it's like an asteroid orbiting the sun, and at its closest point to the sun, let's say the perihelion is going to be 1.55 AU, and the farthest point from the sun, let's say the aphelion is going to be equal to 3.58 AU. And I want to know a measure of how elliptical is the orbit. So the eccentricity is going to be the big number, 3.58, minus the small number, 1.55. That divided by the two put together, 3.58 plus 1.55. Now you can do 1.55 plus 3.58, doesn't really matter. Okay, and so all that you would have to do is enter that into the calculator. It's a good idea when you enter that into the calculator to use parentheses there, otherwise you might not get the right answer. Okay, and that's 3.58 right there. Okay, so the eccentricity is going to be 0.396 for that particular orbit. So that's an example of that calculation right there. Okay. Second law of motion is that the planets speed up and slow down as they go around the sun. So when they're close to the sun, they go fast. When they're far from the sun, they go slow. Mathematically, the areas match each other. And again, the book has a very good diagram and description of that. So it's the law of equal areas. Or you can remember that it goes fastest when it's close and slowest when it's further away. For this class, that's the bulk of what you need to know. If you're actually doing orbital dynamics, calculating, for example, if you were working to send a spacecraft to Mars, you'd have to know exactly how fast it is. So as it goes around the sun, it speeds up and slows down, and so the orbit would speed up and slow down as it goes around the sun. Okay, so it would go around the sun, speeding up and slowing down. Okay, so okay. Now, The closest is perihelion. The farthest is aphelion. So this is the perihelion, and that is the aphelion. Okay. Well, the next law talks about the semi-major axis. Semi-major axis is half of that distance. Well, that's going to be A, the semi-major axis. Well, if you look at it, A is 1/2 of the perihelion plus the aphelion. But what happens if you add two numbers and divide by 2? You find the average. So what happens is that the semi-major axis can be thought of as the average distance from the sun. And so that would be another way of looking at it. So we would say that the average distance of the sun measured in AU cubed is equal to the orbital distance squared. So we can do an example of this. Let's say that we have an asteroid that orbits the sun, and the closest distance to the sun is 1.55 AU, and the farthest distance to the sun is 3.58 AU, and I want to know how long does it take to orbit the sun. Okay, so how long would that be? Well, we know that p squared equals a cubed. So we just need to find A. So A is going to be the average distance. So that's going to be 1.55 AU plus 3.58 AU divided by 2. Okay, so the A, if you do that math, 1.55 plus 3.58 and divide by 2, and I'd say go ahead and do that, make sure you get the right answer. Okay, that's going to be 2.56 AU. So that's A. So P squared is equal to 2.56 cubed. So 2.56 cubed, so you raise that to the third power, and that is going to be 16.8. Well, I want to know P, how long does it take to go around? Well, P is the square root of P squared, so that's going to be the square root of 16.8. Okay, and so if I take the square root of 16.8, then what happens is I get 4.1. So that means that it takes 4.1 years for that asteroid to orbit the sun. So let's do another example here. Let's say that we have these planets going around the sun. So we've got, the sun, we got Earth, we got the planet. And so opposition, and then the next time Earth's in opposition, that's synodic period. Well, we've already, when we were talking about Copernicus, there were equations there that you could use to figure out the sidereal period, the actual time that it takes to go around. So let's say that you calculate that a certain planet takes 84 years to go around the sun. Okay, so do what we did in that previous lecture. Find out how long it find out from opposition to opposition, find the sidereal period. Let's say you do that and get 84 years. Now I want to know how far is that from the sun. Well, Kepler tells us A cubed equals P squared. So that means that A cubed is going to be 84 squared. So use your calculator. 84 squared is going to be 7,056. But I want to know A, how far is it from the sun? So for that, you take the cube root of 7,056. Well, how do you take the cube root? Well, you use the right button on the calculator to do that. Okay, so we want to take the cube root. And so that means that we want to take the cube root of 7,056, and that comes out to be 19.2 AU. So that means a planet or an asteroid or something that orbits the sun once every 84 years has an average distance of 19.2 AU. Now, if you also happen to know the eccentricity, you can work backwards and calculate the perihelion and aphelion. Okay. We're not going to worry about that, but that can be done too. There's an extension to the whole thing. But now we can find the relative spacing of the planets. And this was a huge step forward, because that means that they could then figure out that, for example, that Mercury orbits the sun on an average about 0.39 AU. They could find that Venus orbits the sun about 0.7 AU. They find that Mars orbits the sun about 1.4 AU. They find that Jupiter orbits the sun about 5.2 AU. They found that Saturn orbits the sun about 9.5 AU. Okay, and so this was a major step forward. In fact, you know, it turns out that Uranus orbits the sun at about 19 AU. And so this was a major step forward. They had no idea at the time how big an AU was. They did not know what an astronomical unit was. They knew that's the distance between the Earth and the sun, but all they knew was that Jupiter orbits 5.2 times farther out from Earth. They knew that Saturn orbits 9.5 times the distance the Earth is from the sun. But it took many years later until they figured out how far Earth was actually from the sun. So they had the relative spacing of everything. So again, this is part of the power of this. And then once you figure out that Earth-Sun distance, once you figure out how big an AU is, you can now find the exact distance to all the planets. And so that is where Kepler's laws come in.